In the previous lecture, we talked about linear functions. For a function from R to R, we can write a linear function as f of x equal to a plus bx, while for a multivariate function from Rm to R, we can write f of x equal to a prime x. In the second case, a and x are m by 1 column vectors. And A transpose multiplied by x is the dot product of these two vectors. We may add an intercept if we like to this function, or we could simply restrict, for example, the first x variable to be equal to 1. Another type of very important functions are quadratic functions. For a function of one variable, to make f quadratic, we write plus c times x squared. And what we will discuss in this lecture is what this quadratic term corresponds to in a multivariate function. For a multivariate function, this quadratic term is called a quadratic form. So let's ignore the linear part of the function and let's focus on the quadratic part. We begin by considering the simplest case where m is 2. So I have a function from R2 to R. So I can write f of x as f of x1 comma x2. So the quadratic part, not surprisingly, has some constant times x1 squared plus another constant times x2 squared. But it also has a third term, the cross product of x1 and x2. So we need to add also c3 times x1 times x2. This is the quadratic part of a function of two variables, and it's also called a quadratic form. If I have a function of three variables, x1, x2, and x3, I will have three terms with squares, c1 x1 squared plus c2 x2 squared plus c3 x3 squared. And I will also have all possible cross products between the x variables. So I will have x1 x2, x1 x3, and x2 x3. So now let's try to figure out how we can write this quadratic form using matrix notation. The linear part could be nicely summarized using this notation, a prime x. In matrix notation, the quadratic part will be x transpose multiplied by some matrix A multiplied by x. This is called a quadratic form. Here, A is a matrix and it's m by m, where m is the number of variables in the function. And A will contain these coefficients in front of the quadratic terms. You can check that the dimensions make sense. X transpose is 1 by m, A is m by m, and x is m by 1. So these match, and the final result of x transpose ax is 1 by 1. So it is actually a number. And it should be a number because f is a function from Rm to R. So let's check that x transpose ax actually is a quadratic form containing the squares of the x variables and the cross products. And let's do that for the simplest case where m is equal to 2. So I have a matrix A, could be arbitrary, let's call it A11, A12, A21, and A22. If you calculate A times x, you will get, as always, the left-hand side of a linear system, A12, x2, the second row A21, x1 plus A22, x2. And if you calculate x transpose multiplied by ax, you do the dot product of x and ax, and that will be x1 multiplied by the first row plus x2 multiplied by the second row. Simplifying this result, we have a11 x1 square plus a22 x2 square plus a12 plus a21 x1 times x2. And we see that indeed x transpose ax is a quadratic form with the x1 square term, with the x2 square term, and with the cross product. And we also see how to interpret the coefficient in the A matrix. The diagonal elements of the A matrix, A11 and A22, well, those will be the coefficients in front of the square terms, A11 and A22, while the sum of these two terms will be the term in front of the cross product. If you do a function of 3 variables and you let a be a 3 by 3, you see that the same thing will happen. This term will be the coefficient in front of x1 square, x2 square, x3 square. The sum of these two guys will be the term in front of x1, x2. The sum of these two, the term in front of x1, x3. And the sum of these two will be the term in front of x2, x3. Here is a simple example. Let's say I have a function from Rm to R equal to x1 square plus x2 square plus all the way to xm square. How can I write this as a quadratic form in matrix notation? And what will the A matrix be? Well, in this example, you see that there are no cross terms. There are no x1 times x2 and so on. That means that all the off-diagonal elements must be 0 in A. You also see that the coefficient in front of every xi square term is 1. And that means that every diagonal element of A must be 1. So to conclude, A must be the identity matrix. And we can write f of x as x transpose times I times x. But we know that I times x is the same as x, so this is actually x transpose x. And this should not be surprising. X transpose x, well, that's the dot product of x with itself, and doing this dot product gives me precisely f of x. So to summarize what we've said so far, if A is a square m by m matrix, then the function given by x transpose ax will be a function from Rm to R, and it will be called a quadratic form. And it's the multivariate correspondence of the quadratic part of a quadratic function. The example we considered was the m equal to 2 case with an arbitrary matrix A, which gave us this quadratic form. Now there is an important but slightly annoying part about quadratic forms. Let's consider the quadratic forms of A equal to 1, 2, 0, 1 and the quadratic form corresponding to B equal to 1, 1, 1, 1. To get the quadratic form, we get the coefficients for the quadratic terms from the diagonal, so it's x1 square plus x2 square. Then, to get the cross product, I sum the off-diagonal elements, so this is 2x1, x2. In this case, I get x1 square plus x2 square. And if I sum the off-diagonal elements, it's also 2. So I get 2x1, x2. So what we can see is that two different matrices may actually give rise to the same quadratic form. This happens in the general m by m case as well. This is really because the coefficient in front of the cross product is a sum of two elements in the matrix. The element in row I column j and the element in row j column I. More generally, if I have two matrices A and B, then the quadratic form x prime ax is equal to x prime bx if the diagonal elements are the same and the sum of the off-diagonal elements is equal. And again, a similar result applies to the general case for an arbitrary m. So this means that whenever I have a quadratic form like this one, I have many choices for my matrix which represents this quadratic form. Fortunately, there is a standard choice that is almost always made, and that is to take this coefficient in front of the cross term, 2 in this case, and divide it equally between the off-diagonal terms. So the preferred matrix representation of this quadratic form is B, not A. In general, if I have an arbitrary matrix where the diagonal elements are the coefficients in front of the square and the cross product in front of xi times xj is the sum of these two terms, where the upper one is in row I, column j, and the lower one is in row j, column I. So what we do is we put half of the coefficient in this one and half in this one, making these two equal. The advantage of doing this is that A will then become a symmetric matrix, simply because we have divided the coefficient in front of the cross term such that Aij is equal to Aji, and that is the definition of a symmetric matrix. So if we have an arbitrary quadratic form, x transpose Ax, it is always possible to replace A with a symmetric matrix B without changing the quadratic form in any way. It also means that whenever you see a quadratic form, you can expect the matrix to be symmetric. Next, we'll look at the sign of a quadratic form and discuss what we mean by definite quadratic forms. Remember that a quadratic form returns a number, and for a number we can always look at its sign. Whenever we have a linear function whose slope is not equal to 0, we know that there are values of x which makes this function negative, and there are values of x which makes it positive. A quadratic function is more interesting in this case. We know that we can find a quadratic function which will never take any negative values and always be greater than or equal to 0. For example, f of x equal to x squared. And there are quadratic functions which will never take any positive values. Well, since quadratic form corresponds to the quadratic terms of a linear function, the same kind of discussion applies to them. So if I have a quadratic form x prime ax, we say that it's definite if it takes on only one sign for all possible values of x. In particular, we say that it's positive definite if it's always positive for all x different from 0. The right-hand 0 here is m by 1 column vector where every element is 0. We have to include the condition that x cannot be 0 because f of 0 must be equal to 0. Similarly, we say that it's negative definite if it's always less than 0 for all non-zero x. We say that it's positive semi-definite if f of x is greater than or equal to 0. In this case, you may be able to find a non-zero x for which the function is 0. And negative semi-definite if f of x can never be greater than 0. Finally, for a quadratic form, we say that it's indefinite if it can take values of both signs. For m equal to 1, that is when f is a function of one variable, then the quadratic form is simply ax squared, where a is a constant, and the only two options in this case is that it must be positive definite or negative definite, depending on the sign of a. So here are some important examples. First, if A is the identity matrix, then F must be positive definite. In this case, x prime ax is simply equal to x prime x, which is the sum of xi square, and each xi square is greater than or equal to 0, and it can only be 0 if xi is 0. So you can see that this is a positive definite quadratic form. In general, if A is a diagonal matrix where all the diagonal elements are strictly positive, then for the same reason the quadratic form will be positive definite. Here is another important example. If A is an n by m matrix where n is greater than m, that is A has more rows than columns. If you then consider the linear homogeneous systems of equations ax equal to 0, and you find that this system only has a trivial solution x equal to 0. Well, in that case, the matrix A transpose A must be positive definite. A prime A is here an m by m matrix. So let's try to show this. We want to show that A prime A is positive definite. The quadratic form in this case is x prime multiplied by A prime A multiplied by x. That's the quadratic form. And we want to show that this is greater than 0 for all x except for x equal to 0. Using the rule of the transpose of a product, we can write this as ax transpose multiplied by ax. If you check the dimensions, you see that ax is n by 1. So let's call this v, a column vector. We know that the system ax equal to 0 only has the trivial solution x equal to 0. That means that this vector v can never be equal to 0 if x is different from 0. The final step, we look at this quadratic form and we see that we can write this as v transpose multiplied by v. That is just the dot product of v with itself, so it's summation vi square. This clearly can never be negative to sum of squares, but that's only enough to tell us that it's positive semi-definite. To make sure that it's positive definite, we must convince ourselves that this can never be equal to 0 if x is different from 0. Well, that follows from the discussion up here. If x is different from 0, v cannot be the 0 vector. That is, at least one of the components of v is non-zero. The square of that is then non-zero, and the sum of these terms cannot be 0.